The next chapter is about forecast evaluation. So if you think about evaluation in like a general regression or maybe classification setup, you would usually at first, have your target value that you're training for. So you fit your model towards this target value. You calculate an error. You would usually do quadratic loss or absolute loss. Then you compute an error measure, which means you average over all of these errors. So root mean square error would be the quadratic version, or mean absolute error, absolute version. And then later you do some sort of model selection or hyperparameter tuning. And for that, you would usually use cross-validation. So it's quite established, quite straightforward. On the flip side, for forecasting, it's much more complicated. Right, so it starts with what is actually my target value? Well, do you want to predict one step ahead? Do you want to predict in an hourly series the next day? So that would be then 1 to 24 step ahead. Many different options. Then calculating errors. We also have the absolute and quadratic losses. But then we have many other things like percentage errors, relative errors, scaled errors. That usually has to do with the scaling that is quite difficult in the non-stationary case. We get to that in detail in this chapter. And then when you have all of these errors, you can average over them in very different ways. So you obviously RMSE, MAE are here as well, but then you could do the mean, absolute percentage error, medians, we have geometric means, we have some relative ways of averaging. So many different error measures in use. And also the cross-validation, people do different things. So you would do kind of what I call sometimes last block validation. So you reserve a part from the end of the series for validation, but there are also different cross-validation options without dependencies, many options in every one of these different processing steps. Okay, let's start with data partitioning and model training, which is kind of this last step, this cross-validation step. So we could just do this quite straightforward training and test split, where we split a test set from the end of the series, right, which would be here. I've called that last block evaluation. It's also commonly called just out of sample evaluation in forecasting. And now you can do this in a fixed and in a rolling origin evaluation. So origin is kind of your last known observation. So that this would be the last point in the training set, kind of here. And now if this is fixed, then you predict going forward. So that means you do now effectively a 1 step ahead prediction here. Now you predict 2 steps out, 3 steps out, 4 steps out. And like that, you make the prediction for a whole kind of output window, but each prediction is a different step ahead, right? And then the other option is a rolling origin, where you kind of update your training set, right? So this value that you tested on here, this one here, you now move it to the training set. And then, you can then obviously retrain fully with this new data point, or you can just use it in inference. So that's another distinction here. But the idea is that you always do 1 step ahead. You always predict just the next step, and your origin rolls forward, right? The last known observation is always one in the future. And these two processes are very, very different, right? A fixed and rolling origin evaluation. I have here an example for you with a naive forecast, right? So let's say here's our last known observation. Now we do fixed origin, which means we just use the last observation as our forecast, which is a naive forecast. So we just have this one, and this doesn't change because the origin doesn't change. So this is a fixed origin naive forecast. But in the rolling origin, we update every time we use the last observation. And what that does in the plot is that the forecast just shows as like a shifted version, right? So basically, if you look at this one here, up here, for example, the naive forecast at this time is obviously exactly the known observation, so it's just kind of the signal shifted. And what that makes is that in these plots, it's actually really difficult to figure out if a method is good. The first thing is that I find these plots always quite deceiving, because you see the error is obviously calculated this way, right? But the difference here is always quite small, so it always looks better than it does, right? So if I tell you here, look at the difference between the red and the black signal, they look very close, but keep in mind errors are calculated this way. So in these steep increases, actually the errors are quite large because they are measured vertically. Okay, that's the first thing. They are a bit deceiving to the eye. And the other thing is they are not very useful to really know which method is good, because you've seen the naive forecast already has this trailing behavior in these plots. So if I now ask you, well, is I don't know, the SVM here in this example is, so or let's say the blue one, right? The random forest. Is the random forest better than naive? Okay, so now we need to compare the blue line with the red line. We see here it's a bit worse. Here it's kind of the same. Here it's a bit better. But you see, it's not straightforward at all to know which method is better than the other in plots in rolling origin, right? So that's just a bit of something like a pitfall to watch out for, that these plots for rolling origin can be quite deceiving. For fixed origin, it's usually fine. You look at them and you say, okay, they're a lot more helpful with fixed origin. Speaking about fixed origin evaluation, so it's usually easier to implement than rolling origin. And forecasting competitions mostly operate like this because they cannot disclose the test set, right? Like they tell you, this is your training set, and now this is a test set that I want you to predict, and then you just predict the whole test set without being able to get new data, to get new data available to you. And that's why a lot of kind of academic settings are also fixed origin. But the obvious drawback is that it's not usually how we operate in practice, right? In practice, we would do forecasts every week, every 5 minutes, something like that. And then obviously, we always have the data available up to that point. If we forecast every week for the next week, every week we have the data available up to that week. Another big problem of fixed origin evaluation is that we can only evaluate one forecast per horizon and per series, right? Because we only can do one step ahead, and then the next one would be already, and the next one that is 2 steps ahead. That's a different horizon. And it's also often difficult to capture the full picture. You know, you could have summer holidays, Christmas, and so on. So, for example, in a competition like the M5, a big question would be for you, okay, well, if it's fixed origin, they want me to predict the next 28 days, for example. What are these 28 days? Is there Christmas in there? Are there any holidays in there? Because if they are not, then there's no reason why you would want to model a Christmas effect if you're never going to be evaluated on Christmas, right? So in that sense, also these methods can be a bit unrealistic, because obviously in a real world forecasting system, you would have to handle everything throughout the year. Okay, and now on the other hand, the rolling origin evaluation, this is also sometimes called time series cross-validation, right? So if you read time series cross-validation, that's rolling origin evaluation. The main difference is that rolling origin evaluation usually means you do single steps, right? So, and that would be the same as like leave one out time series cross validation, but then there's obviously also k-fold time series cross validation, where you do not change the origin like in single steps, but in bigger steps. Yeah, this rolling origin evaluation, it can be difficult to implement with some of the more traditional methods, as they would usually be retrained for every forecast, right? So they don't have this idea of updating. It's often an implementation question. But it is very natural with machine learning methods where it's very normal that you have new data that comes in and then you just use a model on this new data without retraining. Right, so here the traditional methods, that's like ETS, ARIMA. So ETS, it usually just fits a new model for with every data point that comes in. Yeah. So, and then, I mean, the way you would do it is with a machine learning model. So you would take single steps, not retraining for a number of steps, and then, but then you would eventually retrain, right? So maybe let's say you have a model that does predictions every day. So you have it forecast for 2 months without retraining, and then you retrain, something like that. So yeah, people would often do this a bit mixed. Yeah, and this is even more important in global models where all the series are in sync regarding the timestamps, right? So what I mean with this is that using rolling origin evaluation is more important in this case because yeah, with the fixed origin, exactly. Like if you do fixed origin, only one test set. If this test set doesn't have Christmas, it doesn't have summer holidays, it's not fully representative, you have a problem. That's less of a problem in data sets like M3, M4, because they are not aligned in time. So some time series would have Christmas in there, other time series wouldn't. So it's a bit of mix across the series anyway. So it's a bit more acceptable to do fixed origin here. But yeah, one thing that is very difficult or quite difficult to deal with in rolling origin evaluation is data leakage from training to test set. Yeah, let me talk a bit about data leakage because it is a big problem in forecasting. It is not trivial to avoid in forecasting. I think every forecaster has at some point produced code that had some data leakage issues. I've done it. My students have done it. Yeah, it's always a big problem. And why is that? Well, that's because in rolling origin evaluation, the data travels from the test set to the training set. So it's really hard to completely separate training from the evaluation code base. Usually you would have both in one code base so that you can easily have this data traveling. Yeah, but then, yeah, there could be data leakage. And the other thing is, well, there could be this obvious data leakage, but there are also more indirect forms of data leakage, right? So usually in machine learning, people would tell you, don't normalize before you split into training and test sets. So don't calculate a mean over all of your data, and then afterwards, you split into training and test set, because obviously that uses some information from the test set for the normalization that you in your training data. But yeah, in forecasting, obviously, same thing, normalization. Don't do it before you split into training and test. But there are also many other things how you can get data leakage. So any form of smoothing or decomposition, if you do an STL decomposition over the whole series, and then afterwards you partition into training and test set, well, STL decomposition does a two-sided smoothing. So data from information from your test data is used then in training. Yeah, feature extraction, don't extract features of your full series before partitioning, yeah, any form of feature extraction. Another method is empirical mode decomposition, which is also decomposition. And for some reason, I'm not too sure why, but many people who use that in papers, in published papers, do it wrongly by running EMD on the full data at first, and then they get amazing results for forecasting. But obviously, they never use their system in the real world, because then they would figure out that it's not usable. Okay, so yeah, let's go back to rolling origin. So you can do that now in two main ways. So you can have this expanding window where you basically say, okay, I have here my training set grows. So with every new data point that I'm getting, I kind of add that to the training set. You can also do fixed window, where for every new point that you're adding, you're kind of deleting one point from the end and make it in this way fixed. Expanding window is better if you have less data available as then the training set grows. If you have tons of data, then often fixed window, you just choose a window the size you want. You can also combine the two. You start with expanding window, and then after some time, when you have enough data, you move to fixed window. Yeah. Okay, now different ways of cross-validation, right? So we have seen the time series cross-validation, but one quite interesting question is, why not just do a normal cross-validation, right? So we've seen this out of sample evaluation, where you have a block of data from the end as your test set here. But if you think about how usually cross-validation is done in machine learning, is you do have this randomly selected folds, right? And now in forecasting in a time series, well, I've given you here an example where the orange dots would be the test sets that are randomly chosen folds in this 5-fold cross-validation setup. So why do people usually not do that? Well, obviously there are problems of serial correlation between the data. So if you just have a data point here in the middle, well, that will depend highly on the data points just around it. And problems of non-stationarity. So if your series has like this trend, then of course using this as a test set versus using kind of this as a test set will be very different. Right, and just using data from the future to predict the past, it doesn't quite feel right, because it's just not how this is going to be used later on. So there's this fear that cross-validation will grossly underestimate the generalization error, right? So obviously it is a lot easier to just predict one data point here than if I tell you, okay, now predict for me like the next 10 observations. It's obviously way more difficult. And another thing is that most traditional methods like ETS and ARIMA, and also recurrent neural networks, anything that has like a state that is updated, they cannot deal well with missing data in the training set that would be missing because it's reserved for testing, right? So it's like you cannot really implement it very well. It has all of these problems, so people have usually not considered it. However, there are some adaptations in the literature. I mean, you could do this block cross-validation, right? Where you say, okay, my folds, I just choose them in blocks. So this serial correlation problem is at least gone. I mean, you still have this general non-stationary problem. And then another thing that people have done is this non-dependent cross-validation, where you say, well, if a data point is in the test set, then I need to remove a neighborhood around it from the training set. Yeah, so the problem is that this non-dependent cross-validation, I mean, you now have to throw away a lot of data that you would really like to train with. So the block cross-validation is quite better in that sense. Still, you have this problem of non-stationarity that that if there's a large trend, for example, a steep trend, that the end of the series looks very different to the beginning. However, the situation is a little bit different if we do machine learning under pure autoregressive setups, right? So if we don't have a state, we don't have any like moving average terms that learn from the error that needs to be updated. We really have just our lags, and we just do this embedded lag matrix, which would be, AR models, but also if you just train light GBM or neural net feed-forward neural networks, like anything that has just an input window and nothing else. There, of course, you can do cross-validation by just kind of picking instances for the test set in this matrix, right? You first do your embedding, and then afterwards you do the train test split, right? And you can also again do that in a blocked way, or here, or leave a bit of a gap so that you don't have dependencies. And yeah, it turns out, that's some work I did in my PhD with co-authors, that we can theoretically prove that cross-validation performs well in this purely autoregressive setup, as long as the models nest or approximate the true model, as then the errors are uncorrelated. So what that means is that it doesn't really matter that we have here like the same value appearing and that there is all of this correlation in this matrix, because once you've trained your model and you look at the errors that you produce, that the model produces, and these errors are uncorrelated, and that's kind of everything that the cross-validation sees, these uncorrelated errors. Yeah, so, well, many machine learning methods work like that. And yeah, so the message here is you can perfectly use cross-validation without any modification to detect overfitting, right? So if you're using some machine learning implementation of a method, it has some internal cross-validation implemented. Yeah, you can use it for in a forecasting scenario. It's not as bad an idea as it might sound at the beginning. Yeah, because it still works fine to detect overfitting, because then your residuals are uncorrelated. And underfitting, you can detect that easily anyway. So it's usually all about detecting the overfitting. Because underfitting, you can detect that just with a test for serial correlation. And this procedure is actually implemented in the CVAR function in the forecast package in R, for example. Yeah, so how do these serial correlation tests work? I mean, there's, for example, this Young box test from 1978 that detects this serial correlation in the residuals. And that then means that the model is underfitting. So you look at the residuals that you are getting. Is there any autocorrelation in there? Are there any seasonal patterns in there? If yes, then your model is not using all the information in the data available, and you should build a different model or pick a different model, right? So the idea is just do the normal random fold cross-validation to detect overfitting, detect the underfitting with the Young box test, and in that way you can actually use all the data, any machine learning implementations for model selection.